Well, in continuation of our earlier video presentation, where we saw this sharing of the edges, and I explained how these edges, this forms the 1 by 8 of a crystal. Okay, so 1 by 8 of a crystal. So you have another cube here, and then likewise you have another cube here, another cube here. Okay, so you can get 1, 2, 3, 4 cubes there. This one, 1, 2, 3, 4. So this particular part will be going here, will be here, will be here, and this one also there. So 4 at the lower level and 4 at the top level, and these give rise to 8 cubes, and we saw how 8 sharing is equal to 1 cube, one particular atom, C atom is there. So if you have some atoms which are larger, it can be accommodated only inside this, right? And depending on the size of the atom, we saw how the types of the crystals are varied. So that was based on the size of the crystal. But here you're going to see about something about the ionic crystals, types of crystals. The first type is the ionic crystals. Some examples are given in which we have cesium chloride, zinc sulfide, and calcium chloride. The arrangement of the atoms is based on the size of the atoms. Here the lattice points are occupied by cations and anions. You know what is meant by lattice? Lattice is having a unit. Okay, so for example, CSCl, that gets repeated. That gets repeated is called as the lattice. So if you have a lattice, then you have something called as the ordered pattern. Ordered pattern of the crystals. And this ordered pattern gives rise to several properties of the solids. That is why solid state exists. And then you have the defects in the solid state. The defects gives rise to some electrical and magnetic property, which we are going to see later. So these are held together by electrostatic attraction, or you can see that some of them will be electrostatic or ionic bonds. Usually what we see is, we have a notion that every line is going to be a bond, but it is not a bond. Only suppose if this is CS and this is Cl, only one will be a bond. Okay. Or if this has a coordination number of 2 or 3, or this bonding capacity of 2, then like in magnesium chloride, one magnesium will be bonded to 2 chlorine atoms only. The rest of for example, if this is magnesium, it will be bonded to one chlorine atom and the other chlorine atom. But you will have the chlorine atoms adjacent like this, and they are not at all bonded. They are not at all bond. They are not bonds. The lines, this line is also a not bond, and this line may be a no bond. Only they are held together perfectly in their place by means of a electrostatic attraction. That is what is being mentioned, electrostatic attraction. And this, because of their ionic nature, are hard, brittle, and have high melting point. Brittle means, once you break it, they break it. I mean, they are hard. They cannot be bent, but they will break if you try to do that. Something like a glass, it doesn't break in a particular order. It's breakable. But whereas rubber is opposite of brittle is ductile, which you can bend, which you can cleave, and which you can take it according to your requirements, right? So they are poor conductor of heat and electricity, the ionic electrons, because you may be having ions like plus and minus and plus and minus, but they're not moving. Okay. Because they are not moving, they do not constitute electricity. I mean, they do not constitute any electrical property or any moment of the same. Okay, so let us see the next part of the slide. There you can see. Then the next is the covalent crystals. Just like ionic bond and covalent bond, you are having the covalent crystals. And here also the difference is, in the earlier case we had ions, and here we have atoms, the types of covalent crystals. So covalent means atoms, lattice means ions. I am sorry, ionic means ionic crystals will have ions. They are occupied by atoms and held together by covalent bonds. Okay, covalent bond is mutual sharing of electrons. Okay. They are also hard, but they have high melting point, but they are poor conductor of heat and electricity. An example is the carbon atom in graphite. Look at this, they are all held together by these covalent bonds. This I am shading all covalent bonds there. Okay. And these are held together by layer by uh, non-covalent bonds. Interactions. So layer is also given there. Okay. Diamond is also a type of the carbon atom based. This we call it as the allotrope, forms of carbon that exist in nature. And this is one of the most basic example. You may even have sulfur like that. After the ionic crystals and covalent crystals, you have a third type of crystals, which tells that it is a molecular crystal, where you have molecules and lattice points are occupied by molecules. Usually, organic molecules occupy this slot, and they are held together by intermolecular forces. This is a very essential point there. They are very soft, low melting point, they are poor conductor of heat and electricity. Okay, so we must be differentiating between atomic, ionic, and molecular crystals. Atomic, ionic, and molecular crystals. So these two are different in a way that they are not molecules. Their property depends on the type of atom there and the type of interaction there. But this one being molecule, now will have molecular interaction and the molecular property. Okay. Then next, coming to the fourth type, we have something called as the metallic crystals. Metals have different property. They are very hard and they are very lustrous, and they are something have good electrical conductivity also. Lattice points are occupied by metal atoms. Okay, and they are held together by the metallic bonds. These usually are covalent in nature, but there may be back bonding from metals, back bonding, and maybe some s, p, d electronic distribution between certain orbitals to give that metallic property. They are also soft as well as hard. Soft means in the sense they are ductile. Okay, they can be bent or they can be molded. Okay, so if I say gold, gold is, if you say we classify them in gold as the 24 karat and 22 karat. If you take 24 karat, it is very soft, and if you can mold it with your hand, it is very ductile and malleable. So to give some hardness to it, they mix it with some 22 grams with 2 grams of copper, and some people mix it with 2 grams of platinum, some 2 grams of cadmium. So this 22 grams of that and 2 grams of some other thing gives rise to hardness of the metal. But as it is, they are very ductile and they are very soft. They can be bent and they can be molded. So that softness is being mentioned here. But some of the metal crystals are also hard. They have low to high melting point. They are good conductors of heat and electricity because of the property, something which I am going to explain in the band theory of the solids later. Okay, this is a cross section of the metal crystal, and there you can see that electrons, that are there here. You have the electrons there. That if you consider it as a nucleus, this is particular atom. Okay, this is one atom, right? This is nucleus. This is nucleus. And then you have the electronic movement around it, around this. Okay. But because you are packed very clearly, this electronic moment can go here. When this electron goes there, electron belonging to this atom may come here. And this may go here and this may come here. And this may go here, this may come here, like this. You can have your movement of the electrons like this, like this, like this, like this. Okay. So it's called as the sea of electrons, and it is also called as the band. Right? This gives rise to the famous, the most notable property called as the electrical property. And this is only possible in only a few cases only. Not all metals are very good conductors of electricity. Okay. So after seeing the different types of crystals, I am again coming back to the lattice types. Then there we have seen already. Here you can see that these are all different atoms. These are all atoms. 1, 2, 3, and 4, 5, and 6, 7, and 8. And the center is another different atom there. Okay. This is now if you consider this as a whole body. If you consider this as a whole body, there is something at the center. That is why we call it as the body-centered structure, and we give the symbol I. This has lattice points at the cell corners, and for body centering, additional lattice points. You don't have to bother about this. Okay. And then every face, every square is considered as a face. This is one face. Okay. This is another face. And this is another face. Okay, like that we have face. Every face is having one center atom. This face is having this, and this front is having this, the back is having this. You may have another cell here at the center. This is also another face. You can have another face centered atom. And is given by the symbol F. This is lattice point, the center of all the unit cells as well as the corners. Even sometimes you can have corners. This is a corner. This is a face. And this line is called as the edge. Okay, so the simplest to give is this one, where you have only at the corners only corners. Okay, within the ionic and metallic types of crystals you'll have these things. This is also known as F center structure, is given A, B, C. And this one, this is the lattice points, corners, and the center of the cell spaces, but in only one plane. So face centered C has points in the AB plane. Face centered B has points in the BC plane. You don't bother about this. It is talking about each thing is considered as a plane. Okay, this is a plane which I am shading, right? And yellow, can be another plane. So if this is A and this is B, it is telling that here you are getting the point that A and B are having atoms. Wherever there is a plane here, so this is the another plane. Here this is having an atom, so he is telling that BC plane is there. Here you don't have any atom, that means the BC plane is not having any atom, so that is being mentioned there. So a classification of that. The lattice types describe the pure transition symmetry of the structure and show equivalent positions within the unit cells related by transition symmetry. Note that the lattice type does not produce definitive information on the number of atoms in the molecule in that cell. That is what I told you. Some are bonds. Okay, some are not. That is, the lattice is the unit that gets repeated. And the type describes the pure transitional symmetry. This is transitional means symmetry. That is BCC is a kind of symmetry. FCC is a kind of symmetry. So how it moves from one place to place, how atom translates to another place is being shown in there, and it tells usually the equivalent points. So that I am going to explain in the next slide there. Okay. So here is an example of nickel arsenate. I think probably you have, most of you have this in the syllabus. 4 units are necessary. 4 units are necessary to see NiAs 6 octahedra in plane view. Okay, this is a plane. What is an octahedra? An octahedra has got 8 faces. Octahedra has got 8 faces. So this pattern is a kind of weaving angle from side. This pattern is weaving angle from top, and this is what is being discussed here. So you see that this is 1, 2, 3, 4, 5 and 6. Okay, that is this. I am marking again. 1, 2, 3, 4, 5, 6. Now they will be arranged in such a way that these two which are left will be going for some other. So you can have, you are having like this, right? It is extended. So this will be forming 5 and 6 of some other next crystal. Next crystal. Okay. And this 1, 2, 3, 4, 5, 6. Right? You see this? 1, 2, 3, 4, 5, 6. This is the same. By this slide, I am asking you to look at the arrangement of atoms. Not only that, how you view, how it is viewed. Okay. So if you just take one particular part like this, it will be appearing like this. Okay. Some atoms may have all the molecules within this. Some may have only within this, and you can see that this is going to be a kind of a, octahedra. Why? This is 1. This is quite opposite 2. And this is 3, and this is 4, this is 5, and this is 6. Okay, so if you draw something like this, it will go like this. Right? And this will be connected like this. Okay, one octahedra. I'm just exactly going to draw this particular octahedra. The red one, I'm just putting the red one there. So it forms a square like this. The red one, green one on top. Here you have blue. Okay, blue at the bottom. So in all, you are going to have 8 faces. This is one face. Likewise, this is second face. This is third face. The back, at the back, we are having the fourth face. Okay, this is the layer above which everything is sitting. So four faces on top, and 4 at the bottom. So the total 4 plus 4 giving rise to 8 faces. and therefore it is an octahedron. Okay, if you view this octahedron from above, from here, if you view it, it will appear like this. Top portion is this one. The edges like this, and this are these edges. Okay. How you view, it gives a different pattern, and that is what is being mentioned there. So after a combination of these, this combination of several molecules give a good crystal structure. Okay, so if you want to do exercise, take up this particular structure and draw it, and here this particular 3 by 4 1 by 4 is all about sharing with the number of units is being mentioned there. Okay, so we'll come to the last part of our lecture here. The same example here, this nickel arsenate that I have taken is given there. You can just go into this, and the definition about this is given here. I am going to take up this and write this in the description part also. In the diagram above means, here that above one as well as this one. Ants are represented by small black balls, while the nickel ions by larger blue balls. On the left to bottom, a layer of S is marked by black balls like 1 by 4. These fractions represent their elevation along direction perpendicular to the screen or paper if you have printed it. Another layer set up by about 3.4 distance. Okay, in the 6 atoms, I have already explained this, and that the explanation is being written there. 6 arsine atoms in the center of the portion form an octahedra. So the octahedra also written, and NiAn at the center marked by 1, 2. In this diagram, the octahedral coordination of only one nickel atom is complete. However, all nickel atoms are surrounded by octahedrons. On the other hand, the 6 Ni atoms are surrounded by As atoms. That is a brief history of, a brief abstract of this is 6 Ni are surrounded by As. 1 Ni is surrounded by 6 As, and 1 As is surrounded by 6 Ni. So all giving director. So in the NiAs structure, the Ni atoms do not form AB or SCP array. So I will explain. AB means first layer is different from the second layer. First layer is different from the second layer. But if you have a third layer also different, then you call it as a ABC layer like that. So AB or SCP array of close pack structure, that is, they do not form the SCP, hexagon close packing. The layers of nickel atoms are directly on top of each other. In contrast, for the NaCl structure, the locations of Na plus and Cl minus are interchangeable. They can change, but in this nickel arsenate structure, they cannot change. That is what is being told. The coordination number for both Na plus and Cl minus are octahedrons. In the upper left diagram, one is clear, then it shows being surrounded by a complete octahedron. This I have explained. This I have explained as a putting the octahedron. Okay, you can see the picture there. So it's not moving. You can see the picture there. Okay, so again you can go back by 20, and here the last paragraph, it says in the upper left only one nickel is shown being surrounded by a complete octahedron, but several arsenic atoms are shown with trigonal prism around them. Again I will explain later. Trigonal prism means, this is the trigonal, if you have something like, again, you call it as if this particular part is prism. Okay, prism is so that is for example, if you have AS here, the center, nickel, 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 nickel will be there. Yeah, this is 1, 2, 3, 4, 5, and 6, and this one is arsenic. So you will, if you look up from above, you will see two triangles in the same directions. In the same orientation. First triangle, this one. Second triangle, the bottom one. Okay, so that is NS. The Na atoms are shown directly on top of each other because it is directly on top. If you see from above, you see this atom is directly above this atom. Okay, but the black atoms are not directly on top of each other in the but arsenic atoms are not. Nickel atoms are on top of each other, arsenic atoms are not. Here is the structure. If they ask you to write the structure of the nickel arsenic, you have to draw it. Again, I am stopping at the structure that is there. So you can see that how this arrangement transforms into the octahedron here. So I even drawn the octahedron here. I'll again explain the nickel arsenic structure in my next class. By meanwhile you can go through again and find out what has been said to you. Thank you for joining me. See you around.